Oh, hey girls, I didn't notice you were there. Let me ask you a question. Who do you think would win if you had one car coming along at 50 miles per hour and you had the identical same car from the other side coming along at 100 miles per hour? Who do you think would win in that battle? Well, that's the kind of questions we'll be answering in this module known as dynamics. More specifically, we're on the module of momentum. No, Tina, I didn't say moment, I said momentum. This isn't your module still, Tina. No, your module has come and gone. Bye. Alright girls, so what exactly is momentum? Let's start with that definition. The linear momentum of an object is its mass multiplied by its velocity. So the momentum of an object depends on those two factors, the mass and the velocity. The more mass an object has, then the more momentum it has. The more velocity it has, then the more momentum it has. If an object is very massive but it is stationary, then it has zero momentum. It has to be moving in order for it to have momentum. So based on our definition of momentum, we have our formula P equals mv. P is the symbol we use for momentum. We use that because mass already has m, so we can't have m equals mv. It will be very confusing, so we use P instead for momentum. So what are the units of momentum? Well, if mass is measured in kilograms and velocity is measured in meters per second, and we multiply the two of those, then we get kilogram meters per second. Something important to remember about momentum is that it is a vector quantity, meaning that both the magnitude and the direction are very important. So let's say, for example, if you were to throw a ball against a wall and it rebounds, it bounces back, in other words, then you have to pick a direction to be your positive direction and one to be your negative direction. Let's say you are considering towards the wall as your positive direction. Then the velocity that it rebounds back away from the wall would be a negative velocity. Let's take a look at an example with Mr. Physics here. Thanks, Mr. Physics. Let me take it away from here. So in this example, we have a ball of mass 250 grams that hits a wall with a velocity of 5 meters per second. It then rebounds at 4 meters per second. What is the change in momentum of the ball? So with problems in physics, I always recommend, wherever possible, drawing a diagram, however simple it may be. So the ball is going towards the wall, it bounces back. Because momentum is a vector quantity, then you have to choose your positive direction. So let's say when it rebounds, in my diagram here, to the left, if I choose that as positive, then initially to the right would have been negative. So I then identify my givens. I know the mass is 250 grams, which is 0.25 kilograms. The final velocity is 4 meters per second. The initial velocity would then be negative 5 meters per second. I then write down my formula, P equals mv. In general, that's how you find momentum. But I'm looking for the change in momentum. So the change in momentum would be the final momentum minus the initial momentum. So I would have mv minus mu. Substituting my values, 0.25 times 4 take away 0.25 times negative 5. So that will give me 1 take away negative 1.25, which gives you 2.25 kilogram meters per second. Back to you, Mr. Physics. Thanks, Mr. Physics. So next thing we want to look at is how momentum is related to Newton's second law. You may recall that Newton's second law states that force is equal to mass times acceleration, but it is also related to momentum. We previously learned in our topic of kinematics, our equations of motions, that acceleration is equal to the change in velocity divided by time. So if we substitute that into our formula F equal ma, we will have force is equal to mass times the change in velocity over time. But the change in velocity we know is v minus u, the final velocity minus the initial velocity. So if we then were to expand the brackets, you would have mv minus mu. But what is mv? That is the final momentum. What is mu? That's the initial momentum. If we take the change in momentum, which is represented by the difference between the two, and divide it by time, then that is known as the rate of change of momentum. So Newton's second law can be stated a second way. Force is equal to the rate of change of momentum. Now, Whenever you have a high rate of change of momentum, then the force is big. What do I mean by that? Let's take a look at a couple of scenarios. Let's say you're driving along and then all of a sudden another car comes in front of you and you crash into that car within less than a second. You're going to experience a great force that smashes you into the other car. That is because the rate of change of momentum was high, meaning that the car came to a stop in a very short period of time. A short period of time means that it's a great rate of change of momentum. On the other hand, let's say you're driving along at the same speed as before, but all the way down the street you see that there's an obstruction. So you press on the brakes and you slowly come to a stop. Do you feel the same amount of force acting on you? Is there the same amount of force acting on the car? No. Why not? Because the same change of momentum took a much longer period of time to occur. So since there is a longer period of time, then we say that the rate of change of momentum is less, and therefore the force that you have experienced is also less. So let's recap that. When there is a long period of time, there's a slow rate of change, so that means there's a small force. And when there's a short period of time, the rate of change is high, so there's a great force. This comes into play, let's say, when you're looking at softball. If you've ever caught a ball before, you know that you shouldn't just catch the ball smack like that. When you play softball, you catch the ball by having it reach your palm and then you slowly bring it down like that. Why do you slowly bring it down like that? Because then you are extending the time over which the force acts on your hand. Therefore, if it's spread out, the force felt is smaller. Now, let's go to an example with Mr. Physics on the board. Thank you, Mr. Physics. Alright, let's do this last example here. So let's say we have a car of mass 5,000 kilograms that is traveling along at 25 meters per second. What force would act on the car if it is brought to rest in half a second and 10 seconds? So we identify our givens. The mass is 5,000 kilograms. The initial velocity is 25 meters per second. The final velocity is 0 meters per second because it is brought to rest. So let's see. We have our formula F equals to mv minus mu all over t. Substituting our values, 5,000 times 0 minus 5,000 times 25 divided by 0.5. So that will give you negative 125,000 kilogram meters per second divided by 0.5 seconds. That works out to negative 250,000 newtons. Here you might be wondering, why is it negative? Well, the answer for that is because it is a force that is slowing down the car. The force is acting in the opposite direction of the car in order to slow it down. So that's why its sign is negative. If it occurs in 10 seconds, well, we don't have to go through the whole steps again. We just can use the same change in momentum value, which was negative 125,000 kilogram meters per second, and instead divide it by the different time of 10 seconds. So when we do so, we get negative 12,500 newtons. Comparing this size of the force with that size of the force, this is 20 times as big. The force experienced is 20 times as big because it took 20 times as short the amount of time. Alright, so once again, you see how the time it takes for the momentum to change will affect the force that is experienced. And that's your lesson for today. See you in class.